Yes, perfect.
Right, so here is a DNA knot, and here is the knot tables up to a point. And your task is to find out where this knot is on the knot table. I'm assuming we're not quite starting yet, so you could look at this, whoever is here, and see if you can find out where this is on the knot table. I will give you a guide to discriminating over and under by walking along this knot. This goes over, then under, then over, then under, then over, then under, then over, then under,
It's
then over,
alternating.
over, under, alternating. And a lot of the crossings are very clearly what they are, and one or two of them require a little judgment. It's a photomicrograph that was made in the 1980s, electron micrograph, of knotted DNA. First proof that everyone would accept that DNA could be knotted by Cosarelli, Spengler, and Stasiak.
Is RNA or DNA?
I'm sorry?
Is RNA or DNA?
It's DNA.
Is DNA.
DNA coated, closed circular, and it's been coated by a process with protein to make it thicker. But it's got how many crossings? 1, 2, 3, 4, 5, 6. So it must be a 6-crossing diagram here. It's a 6-crossing diagram. And there are 3 candidate 6-crossing diagrams in the table. So it should be one of them.
Is it 6-2?
Yeah, 6-2. Right. It's still kind of thrilling to actually, realize you put your eye back and forth between these two and realize, oh yes, this artifact of very complex equipment observation in a micro world comes out as one of the knots on the table. Well, maybe I should consider this the beginning of the lecture. The table, you will find this table in the Dropbox corresponding to the course. So if you wanted to use a knot table, you can use this one. This table is a descendant of the original knot tables that were produced by Tate and Kirkman and Little in the 19th century. They were commissioned by Sir William Thomson, that's Lord Kelvin, to make tables of knots, because Kelvin thought that atoms were knotted vortices in the ether. Well, we'll talk about that some other time, but the ether theory disappeared after a while, and so the knotted vortices in the ether were not considered as models for atoms, but knots and very microscopic physics are still interrelated, something to talk about later. Knot tables are very useful for us as sources of exercises. Let me explain. We have worked out the coloring structure for 3-1, that's the triple knot, and for 4-1, the figure 8 knot. And we have some other comments we should make about that, which I will. You could, if you take the knot table, grab another knot, like maybe 6-1, 6-2, 8-8, and or whatever, and figure out the coloring structure for it. And For the small ones, you can do it by hand by just putting on a 0 and a 1 and propagating colors until you find a modulus. So let's do an example or two of that. So I'll leave this up. I'll let go of the DNA. Maybe I want to keep this file, but let's get a drawing board and see what we can do. Okay. So we made some multiplication tables. Maybe I should recall sorry, this will take me a moment because of the lookup I need to do. Yes. Oop. So we got to 20. I want to go back to maybe 15. Yeah, let's just review where we were last time by going through the last few slides. We were saying things like, well, if we wanted to write down the quandle that would be associated to a given link, like the hop link here, then we write down one relation for each crossing. In the hop link, that's quite simple. We have A bumping into B, so A times B is A. And B times A is B. So the quandle is given by A and B, such that AB equals A, and BA equals B. But what would happen if you were to decide, I'll write it on my own slide. What would happen if you were to decide to go through the coloring, the Fox coloring for this same link? So then you might try A and B again. I'll use the same letters, A and B. But now you have that 2B minus A is equal to A. And 2A minus B is equal to B, right? Where what I'm using is the Fox coloring method, which we talked about before, which does give us a quandle where we have A, B, and C like this, and C is going to be equal to twice B minus A, and this could be over the integers or over the integers mod n for some n, right? This is Fox coloring, as we called it. And it is a quandle. In general, the operation 2b minus a is a quandle operation. So over here, we have the equations, and this says that 2 times b minus a is equal to 0, right? So this implies that we are looking at z mod 2z, right? Which I write as z2. So our quandle is two-element quandles, 0 and 1. And in fact, if we were to do the coloring, I'm going to run out of space here. I might call this one 0 and this one 1, and then 2 times 1 minus 0 is 0. And 2 times 0 minus 1 is minus 1, but minus 1 equals plus 1 in z mod 2z. So this is a non-trivial coloring of that link. And the multiplication table for our quandle is 0, 1, 0, 1. 2 times 0 minus 0 is 0. 2 times 1 minus 0 is also 0. 2 times 0 minus 1 is 1, and 2 times 1 minus 1 is 1. And now you see something interesting in relation to a question that was raised in the last time. The rows are not permutations of the elements of the quandle. There's repetition in a row, but the columns are lists of all the quandle elements. So that, in fact, is what will happen in general. But let's find out what does happen in the case of the modular arithmetic Fox-type quandle. So this is a nice little example of somebody where the Sudoku method wouldn't work if you were trying to get rows and columns. All right? Now let's see what, I'll come back to this, but let's see what else we have in a review from last week. So let's open another one. This was, whoops, I forgot which one it was. Oh, sorry. I pushed a button that I didn't want. I'm sorry, I'm going to have to stop sharing and fix this, so let me just do that. I don't want the chat. And then we'll go back to share screen. Yeah. All right. Okay. $15. Yeah. And then we talked about how to make that linear quandle, and we pointed out that it could be derived. All right. That was that slide. Then sorry. Then I told you about Fox coloring. And then I told you about the min coloring question. And we actually talked about that. All right. Okay. And we talked about this. But let's look at it again from here. So we understand this. And then I gave you an exercise. And it's interesting to do this exercise. I think you'll find it quite easy, so I won't bother you with it, but maybe in the margin. Maybe it's a good idea to look at it in the margin. So we're defining an operation. It's motivated by algebra, strictly for us at this point. But I want you to know, and you can check, A times A is A inverse A, because this is a group multiplication, and here we're defining the quandle operation. So A times A inverse is the identity, and you get B. So, I'm sorry, you get, if it's A times A, then you get A, right? A times A is equal to A inverse A, which is equal to A. Works fine. And what about A times B and then times B? I'll leave the last one for you, but let's do this one. So this is B, times the inverse of A times B, which is B, A inverse B, and then you take the inverse of that and you multiply by B, but the inverse of the product of group elements is the same product in the reverse order with inverses, so we get B inverse A, B inverse, and B, and this is a group, so everything is associative, so this is the same as A itself. And that's what we wanted to check. And then the last thing that you want to check is that A times B times C is equal to A times C times B times C. Now, there actually is a geometric interpretation of this quandle in relation to knots and links, but I'm not going to talk about it now. Later, I hope we come back to it at some point. But you can notice the following, and this is interesting, and does constitute a motivation for this rule. Let me just give you a command here. My command is abelianize. Okay, so if you follow my command, abelianize this, turn the group into an abelian group, write it with a plus so it's easy to see. That means this becomes minus A, and you would have B minus A plus B, right? And that's equal to twice B minus A. So you see that this rule, this quandle rule, is a generalization of the 2B minus A rule. Okay? The item that I actually wanted must be earlier in our slide. Let me see if I can find it. I should have checked where it was before. Maybe, at 14? Earlier than that. There we go. Okay. So by Sudoku, we worked out the whole multiplication table, 5-element quandle associated with the figure 8 knot. Remember how we did it? We said, let's see. We said, we have these relations. A times C is equal to B. I'll circle them. And we have B times C is equal to A. These are coming from the diagram. D times A is equal to C. D times A is equal to C. C times A is equal to D. D times B is equal to A. A times B is equal to D. BD equals C. And CD equals B. That's not everything, but we also have A times A is equal to A, B, C, D, E, because of the axioms for the quandle. And then we said, let's assume that the rows and columns are all permutations of the quandle elements. Let's assume it. And then we could say, well, we've used up A, B, C, and D, and what would A times D be? It must be some new element because we've already used up too many things. And then we figured out that we'd better add an element E, and then we figured out that that should be C, and we went through and filled in the blanks and got the multiplication table, and we found out that it worked. And not only does it work, but it is isomorphic to the Fox Z5 quandle for the figure 8 knot. which you can easily check if it wasn't in the notes, and I don't remember whether it's in the notes or not, but if you work out the Z5 quandle and compare the multiplication tables, you see that they're the same. Quite interesting. But now we have the question that came up. And let me try working that question in this same set. No, I think I'll start a new set. Okay. So okay, so that'll be lecture 4, and we'll put, well, we can keep it going in there. All right. So we have the following question. When are the rows permutations? Right? So we're thinking of a multiplication table. And we have the quandle elements, A1, A2, A3, and so on. And we have some element B. And here you have B times A1, and then you have B times A2, and so on. And we want to know, when is this a permutation? So that means we want to know what happens if B times A is equal to B times A prime. What does that imply? So case 1 for us, we can test on something simple. Let's suppose it's a Fox quandle, Fox colored quandle. The 2B minus A. All right? So then we would have 2A minus B equals 2A prime minus B. And that implies that 2A equals 2A prime. So it implies that 2 times A minus A prime is equal to 0. If these are equal, then 2 times the difference between them will be equal to 0. So, moral. If 2 does not divide n, we're using z not n for the ring, then A equals A prime when B times A equals B times A prime. And so therefore, when 2 does not divide n, then the rows are permutations. So that's a partial answer to the question, right? That tells us that if we were trying to figure out the multiplication table in the mod n, you can do it by Sudoku. What about the columns? Let's just put the remark in a small box here. The columns are always permutations. Because what's the column question? The column question is B times A equals B prime times A, right? That would be 2 elements in the same column. But that is true if and only if B times A times A equals B prime times A times A. And that's true if and only if B is equal to B prime. So you see that's just true in any quandle. In any quandle, when you make the multiplication table, the columns will be permutations. That says that the quandle is acting by permutations on the columns. And it's worth looking a little more closely at that action. That's going to be related to a group in general, like that. But we know the columns are always permutations, but the rows are not. But if 2 doesn't divide the modulus and we're in the Fox color quandle, then it will work. So that explains why it did work in the case of the mod 5 situation that was happening with the figure 8. But in general, you don't know, unless you know some extra information, whether or not there would be permutations in the rows. Now, what if we took another example of a quandle type that we could work with? What if we took A times B is equal to B, A inverse B? And then we ask about the row problem. So the row problem becomes, we're going to look at A times B equals A times B prime and compare them. So that means B A inverse B is equal to B prime A inverse B prime. And now we can't solve something like we did when it was 2B minus A equals 2B prime minus A and get rid of the A. The A is stuck in the middle. And so you can think about what groups. So if in your group something was happening that was very nice, then you could see that this would be true. So we could play around with this. Suppose I multiply by B prime inverse B inverse. Then I would have A inverse is equal to B inverse B prime, A inverse B prime, B inverse, right? So I have A inverse is equal to beta, some element of the group, A inverse, beta inverse. No, not beta inverse. Beta, what shall I say? It's just the reversed order product. Sorry. Let's think. I'll erase you think. So what do we have here? This is what our equation is, and I multiply by B inverse on both sides, and then I have B inverse B prime here, and I have B prime B inverse here. Not the inverse of that, but just a special group element. I guess I want to try another. I'm looking for a way to express this, so let's try a different way. Let's write it as A inverse times B times B prime inverse is equal to B inverse B prime A inverse. That's okay, right? I just multiply on here B and then B prime inverse. Now, still not the inverse. So, needs thought. it would work. We could analyze it if the group was abelian, but maybe we can think about groups that are not quite abelian, but have some interesting property that would allow you to conclude that B was equal to B prime under these circumstances. I leave it to you to think about that. Okay, so the next item is this exercise that I suggest to you of taking somebody from the table and trying out the coloring on it. So, for example, I could take 5-2 from the table. Where's our table? We can find it again. Well, you don't need it. I'm just going to draw it. But if you look at the table, this is 5-2. All right, that's 5-2. And I'm interested in finding out about coloring 5-2. So, as I say, one way to investigate this, and it's quite interesting, you just choose a knot from the table and give it a try, is to just start with a 0 and a 1. Of course, that's not the most general case. You really should start with an x and a y and propagate around and get a system of equations. But you can start with 0 and 1, and then 2 times 1 minus 0 is 2. 2 times 2 is 4 minus 1 is 3. 2 times 3 is 6 minus 2 is 4. 2 times 4 is 8 minus 1 is 7. 7 and 0 are communicating, so we must be in Z mod 7. And then you can take a look at what you've colored. You've used, you're going to be in the modulus 0, 1, 2, 3, 4, 5, and 6. And what have you actually used here? You used 0, you used 1, you used 2, you used 3, and you used 4. But you didn't, in this case, use 5 or 6. So, so that means that if you wanted to investigate the whole quantile table, you've got a good chance of perhaps getting closer if you added 2 more elements, and then you could go ahead and try that. So you can also write down the entire system of equations here and work out the whole story about this. I'll come back to the matter of the whole system of equations in a moment, but let me show you one more example. Let's look at 6-2, which was the DNA. So 6-2 has this diagram. And again, I'll try this out. 0 and 1, and that's going to be 2. 2 times 2 is 4 minus 1 is 3. Let's see, 2 times 0 minus 1 is minus 1. I work over the integers until I have to go somewhere else. 2 times 3 is 6, minus 1 is 7. 2 times 7 is 14, minus 3 is 11. There we are. So now we have Z mod 11. And with Z mod 11, you'll see that we have left out 1, 2, 3, 4, 5. 5 new elements. What you see when you start looking at particularly alternating knots, you will find out that the modulus that you get grows rapidly, and a relatively small alternating knot has an enormous modulus, much bigger than the number of colors that you can use to color the knot in its minimal diagram form. So that question that I mentioned before of least number of colors raises its head and wants to be answered. There is another property that you see here, which is that it was a conjecture. It was a conjecture of myself and and Frank Harari, our conjecture was that if you have K alternating and the modulus n equals p, a prime number, then all the colors on a minimal alternating diagram of K are distinct. I think we surprised ourselves with that guess. It turned out that it was true. I proved it for rational knots, the class that I'll tell you about, but it was eventually proved in general by Mattman and Solis. As you see in these examples, that's what's happening. You're not seeing the same coloring of color appearing twice anywhere. All the colors are different in this mod 7, mod 11, or mod 7. And you could look up the Mattman-Solis paper, or you could try proving this for yourself. It's a curious combinatorial fact. So not obvious what it means topologically, but it means something. Let's talk now about getting our coloring in shape, in the sense that what is the method of finding out what the modulus is for any diagram, not just by experimenting with numbers on the diagram. So let's go back to the trefoil knot to illustrate. So I use trefoil because trefoil doesn't give me too large a system of equations. But what I'm doing for trefoil, you could do for any knot diagram whatsoever. You label every arc, and then you write down an equation from each crossing. So the equation from crossing number 1 is 2a minus b equals c. The equation from crossing number 2 is 2c minus a equals b. And the equation from crossing number 3 is 2b minus a equals c. Of course, another way to write this, which might be better for these purposes, would be if you have x and you have y and you have z, you could write x plus y minus 2z equals 0, right? And that would all be on one side of the equation. So in this case, this is b plus c is 2a, a plus b is 2c, a plus c is 2b. And put it on that side of the equation. So we have a system of equations, and we're trying to solve it over the integers or over a modulus. So let's look at what the system of equations looks like. I have the equations for a, b, and c for crossing number 1, crossing number 2, and crossing number 3. So for crossing number 1, I have 2a minus b minus c equals 0. Crossing number 2, I have 2c minus a. Oh, excuse me. We're running the matrix form of a system of equations. So I have 2a minus b minus c. I have 2c minus a minus B. And I have 2B minus A minus C. So this is our system of equations. And then, as I have remarked to you, it's a redundant system of equations. Any one of these is a consequence of the other two, as you can do an exercise to check. And so if we are, and I want to put it another way as well. Let me make it as a statement. We can choose one edge and call its color 0. The reason is as follows. If I have a coloring x, y, and 2y minus x, I think we said this before, but it's worth saying it again. I could look at what happens when I multiply by a constant all the colors, or if I add something to all the colors. So let's look at each in turn. Multiply k by a constant, and you have kx, ky, and then you have 2 times ky minus kx. And everybody has been multiplied, including the third color, by k. So this is still a coloring. If this is a coloring, that's a coloring. On the other hand, what if I changed x by x plus n for some n? And I change y by y plus n for some n. Then 2y plus n minus 2x plus n is 2y minus 2x. I'm sorry, plus n. I mean, I get 2 times, let's look at it, 2 times y plus n minus x plus n. And what do you get when you write that out? You get 2y minus x, okay. 2n minus n is n. So that's cool, right? That says that if it's colored xy and 2y minus x, then it is also colored x plus n, y plus n, and that color plus n. So if you have a coloring of a knot, and you can shift it to another coloring by adding a constant color to any colors that are there. That's such a nice property that it's worth seeing an example. Take the truffle knot, color it mod 3, 0, 1, 2, mod 3. I believe you'll see that that's a coloring, right? 2 times 1 minus 0 is 2. 2 times 2 is 4 minus 1 is 3, which is 0. Now add 1 to all the colors. This becomes 1, and this becomes 2, and that becomes 3, which is equal to 0. And it's still a coloring, you see? That's what I'm saying. So that means that I could, if I want to, just choose one edge, like A, and decide that it's 0. And then I don't have to have any equations for A, and I only need the other equations, and A is 0, and I am reduced to this little matrix here for the colors. So assuming that the color A is 0, I'm reduced to this submatrix, which I will call M. And now I need to figure out what I'm going to do. So let's consider that and go to the next slide. I want to save M. There's our M. So I'm just using that to remind me what M was. M is equal to the matrix minus 1, 2, 2, minus 1. Okay. And what we are concerned with is because we're assuming that A is equal to 0 by assumption. So our system is M times AB should be equal to 0, 0, mod n for some n. Right? But we don't know what n, right? We want to find out what is the appropriate n. And now comes a little bit of matrix algebra. Given a matrix M square, there exists M tilde equals the adjoint of M, such that M tilde times M is equal to the determinant of M multiplied by the identity. You may remember this from linear algebra. For example, if M is equal to A, B, C, D, then M tilde is equal to D, A, minus B, minus C. Check it. AD minus BC, that's the determinant. A minus AB plus AD, 0. CD minus CD, and AD minus BC. So this tells us that M tilde times M is congruent to 0, what we want, when we work over Zn, where n is equal to the determinant of the matrix n. What's the determinant here, by the way? The determinant here is 1 minus 2, which is minus 3. So that's perhaps not surprising, because we knew that we should be working in mod 3 for the triple knot. But what does this say? This says that M tilde multiplied by any column of M is congruent to 0 mod n. So any column of M tilde, I wanted it the other way. Any column of M tilde is a coloring solution. I misspoke myself. Let me fix the slide and we'll say what we need, right? Because it doesn't matter. It does matter. I want M times any column of M tilde. And the best way for you to think about that is if I wrote this, which works in both orders, but I should write it this way. Okay? There we go. So M times the adjoint is the determinant of M times the identity. We're looking for solutions to M times somebody is congruent to 0. But M times any column of the adjoint matrix is going to be 0 mod n. And that gives me a collection of color solutions for my knot. Very easy in the case of the trefoil, no problem. But if you have a large knot, you see that this is a simple linear algebra problem to do. You need on your computer to set up the matrix M, to find its determinant and find its adjoint, and of course, on a computer, m tilde is equal to the determinant of m multiplied by the inverse of m. That will get you the adjoint immediately on your computer, which calculates inverses and calculates determinants, and this will be integral again after all that. And so you can look at the columns of this. So the columns of this matrix, use the computer to compute m inverse, multiply by the determinant, make sure you've got integers when you're back here, and those are the colors. I'll leave it to you to try this algorithm out on something larger for next week. Just try it on something larger, go to the tables and take a 9 or 10 crossing knot, and write down the matrix and hand it to your nearest computer and see what you get. And I'll do the same with some example and show it to you next time, okay? But I hope this is clear. Let's just do part of it on the trefoil matrix. Here's Rm, right? And we want the adjoint. And remember that if m is equal to a, b, c, d, then the adjoint has the formula dA minus b minus c. So for 2 by 2, that's easy. M tilde is minus 1, and minus 2, and minus 2. So that's telling us that it should be the case that for the trefoil knot, if you use 0, then you could use minus 1, that was b, and minus 2, or you could use 0 and minus 2 and minus 1. And of course, that's correct, mod 3. Not so interesting, much more interesting if you did a larger example. So I'm suggesting you try it out on a larger example, and I will, and you can, we can compare notes on what it's like to calculate these things. It is a fact that the absolute value of the determinant of m is an invariant of the knot. For that, you have to settle down and look at something a little more carefully. You have to, for example, you could do it by examining how the determinant of m would behave under Reihmeister moves. I won't try to do that here, but I've given you quite a bit of work to play with this kind of an example. So let's leave it at that and go on to talking about oriented quantals. So I'm going to talk about oriented quantals in a combinatorial way, and then we'll talk about the fundamental group today and see how these are related. In an oriented quantal, I'm looking at an oriented knot. So instead of just having an unoriented species, I have somebody like this. Or maybe more interesting, when you just even go up to the next knot, with the figure 8 knot, you see that the signs of the crossings are not all one type. Here, we're talking about having crossings with orientations. And when we do, then you see that we're going to use the convention that this is a positive crossing and that's a negative crossing. So that in the trefoil knot that I've drawn here, these are all positive. But in this figure 8 knot, what do we have? This is positive by that convention, and this is positive by this convention. But this is negative, and this is negative. So the total here is 2 minus and 2 plus, and the total here is plus. So in an oriented situation, I'm going to define a quandle with 2 operations. I'm going to add A and B going to the right, and here I'm going to add A times B. I'll write it the same way. But if it goes the other way, then I'm going to have an opposite operation, A star bar B. Okay? And then we can figure out, if we're keeping track of orientation this way, what the rules should be for such things. After all, if you had something like this, then you would have an A coming into an A and it should go out as an A, and this would mean A star A equals A. And if you had the opposite kind of crossing, like this, then this would be A, and this would be A. I really wanted this. To stay with my convention similar to the other cases. But you see, if I had a crossing like this is coming up and meeting it going to the left, and it's A, and it's A, and this would be A star A, so I want this. But this says A star bar A is equal to A. So I need these 2 facts. That I certainly need. And what about the Reidemeister 2 situation? A, B, be reversed. A star B, but then I get A star B star bar B. So I need that this should be equal to A. And of course I need A star bar B star B will be equal to A. So that's 1 and 2. And then from the third Reidemeister move, you're going to find the same story, but you need it for each of the operations. You're going to need A star B star C, A star C, star B star C, and A star bar B star bar C should be equal to A star bar C star bar B star bar C. So this is an oriented quandle, an algebraic structure that satisfies these rules. And if we go to this, we actually get stronger invariants of knots and links, and we come closer to having topological interpretations of these that are direct. So let's continue now. Any question about these rules, we'll see them actually happening in some examples in a moment. So here's an algebraic example. G is a group, and we define A star B to be equal to B inverse AB, conjugation. It looks like the previous one, but this is actually a more frequent sort of operation in groups, conjugation by an element. And if I use star bar, it's going to be conjugation by the inverse, CA the inverse. All right? And I claim that's an oriented quantal structure. And let's just do the exercise quickly, at least up to a point. So A star A, that's fine. A inverse A is equal to A. And A star A, bar A is A inverse, and that's also equal to A. Fine. What about the second one? I'll just write it out. A star B star bar B. Let's do that one. So that's equal to B inverse B A B inverse B, right? Conjugate in the reversed way, the conjugate. But of course, the group is associative, and so this goes away and becomes A. And just for fun, let's do the other one. So we have A star B star C. So we get C inverse times B inverse times A times B times C. All right. And in the other way, A times C times B times C is going to be equal to B times C inverse A times C, which is C inverse AC, right? That's A times C, times B times C, and then I have to write that out. And I get C inverse BC inverse times C inverse AC times C inverse BC. And working out that inverse, I got C inverse BC, right? I write it in the opposite order with the inverses. C inverse B inverse C, C inverse AC, C inverse BC. And now these inverses will kill each other off, and these inverses will kill each other off. So this will be C inverse B inverse A, B, C. And that's equal to that's equal to this. So we're done, right? Conjugation self-distributes. Conjugation and reverse conjugation both self-distribute. Remarkable and important fact. So here's a quantum for you. Now I want to talk about the fundamental group. Now, I don't know whether you're used to the formalism of the fundamental group of a topological space. So let me review it quickly. We can speak of the fundamental group of a topological space X. I need a chosen point P in X called the base point, and I will assume that X is path connected for simplicity. And then the idea is as follows. I have the point P, and I consider a loop, which is path, which goes out and comes back to P, like that. A loop alpha at P, meaning it starts at P and it ends at P, and it's a continuous mapping. The loop alpha is a mapping of the interval 0, 1 into X continuous. and alpha of 0 is equal to alpha of 1 is equal to p. So now what I'm going to do is I'm going to multiply loops. So if I have a loop based at p, and I have another loop based at p, then I obtain a new loop, alpha beta, which means run along alpha, then run along beta. All right? And then I'm going to tell you that two loops are equivalent if you can deform one into another, but I have to say this on my slide, don't I? Then we're going to make a group out of it by having it happen that the relationship that I define makes these invertible. So I say that two loops at P are homotopic if there exists F taking a square into X such that F of 0 t is equal to alpha of t, the loops alpha and beta, and F of 1 t is, I would like to do the second coordinate, I'm sorry. Is beta t, and F of TS is a loop at P for all F belonging to the interval 0, 1. So what that means is the following, that we have the following picture. We're mapping this square in, and along the bottom, we have alpha. And along the top, we have beta. And this entire edge goes to P, and this entire edge goes to P. So that if you were to take any intermediate line, this would be F of something S, where S is this distance here, that would also be a loop. So this means that you have a continuous family, this is continuous, it means you have a continuous family of loops that starts in alpha and goes to beta. So for example, suppose that your space was an annulus. A circle across a unit interval, an annulus. And suppose that this is your base point here, right? And let's suppose that you, at this curve, it goes around for a while, and then it comes back. It doesn't go all the way around the hole. It comes back to the origin, right? Well, then you can see that you can put this loop alpha into a family of loops by contracting it. Each one is continuously varying from the preceding one until finally you get down to one loop which is just beta. Here I can have alpha looking like that, and I can have beta of t is equal to p for all t in the interval 0, 1. And here, alpha is homotopic to beta. I write twiddle for homotopic. So that's the equivalence relation I'm going to put on the loops. I'm going to let myself deform them. But of course you see that it's quite possible to have another situation like the same annulus here, and another loop which is not likely to contract at all. We could start at the same base point and go all the way around and come back. And if you tried to contract this loop, you run into the fact that the missing region here doesn't let you continuously deform the loop over that region, and in fact you won't be able to. It's not homotopic to the trivial loop. This is the trivial loop. Now, I may be, for some people, repeating things that you know very well. Let's just spend a few minutes and say these things out loud so that we have them. And now we need to say a bit more in order to get the fundamental group, of course. Let's see. So I start with L of x at P, which is equal to all loops at P on X, which is equal to the set of all alpha taking the unit interval in X such that alpha of 0 is equal to alpha of 1. And then I define pi 1 of xp to be equal to L of xp mod twiddle, where twiddle is equal to the equivalence relation homotopy of loops. And then our claim is that pi 1 at xp is a group, and that it is an invariant of x. And in fact, more to the point, if you have h taking x to y continuous, then there exists a natural extension h star taking the fundamental group of x at p to the fundamental group of y at a to p. And H star will be an isomorphism when H is a homeomorphism. These are naturality properties of our definition of the fundamental group. Now, I want to discuss why it's a group, I'll leave the naturality properties out. We could talk about them a little bit more next time. They're the easy part, but seeing that it's a group is worth understanding. And then I want to show you what the fundamental group, the complement of a knot looks like. So, if I have a loop, alpha of t belonging to 0, 1, then I'm going to define what will turn out to be its inverse, alpha bar of t, and that's defined to be alpha of 1 minus t. All right? And that's still defined on the interval 0, 1. It just starts in the other direction and goes backward. So if we wanted to understand alpha bar, then we just start here and go that way, right? And go all the way back to the beginning. Now the claim is that if you do alpha and then you do alpha bar, it's the same as if you did nothing up to homotopy. And the reason is the following. I have to tell you about what it's like to multiply two loops first, just the geometry of that. So here's alpha times beta. And you see, when I look at alpha times beta, I can deform it a little bit if I want to. So I can deform it right in there as it comes in towards the base point and comes back out. And I can make it look like this. Instead of going all the way to the base point, let's go part way and then I come right back along beta and continue on like that. So this is gamma, and alpha times beta is homotopic to gamma, where it didn't have to go all the way back to the base point. It can just come back nearby and then come right back over, and you can see how to manufacture that. I'll say this more carefully, but the point is that if you multiply a curve by its reverse, I can draw that reverse by just drawing it in parallel to itself and coming back to base point. So this is equivalent to alpha alpha bar, where I deformed it a little bit. Now I deform it a little bit more. I go all the way out, but I don't go all the way to base point. I just go part way and I'm parallel and come back over here like that, you see? And then I'm going to do this even a little nearby, right? Just keep contracting that, right? Until finally I have this, and then I have this, and then I have this, and finally I have the identity. So what I get is that alpha star alpha bar is equivalent to what I'll call E. And E of t is equal to the base point for all t. Okay? So that's going to be my identity. You'll see that it is an identity. Times alpha bar is equivalent to the identity element. And that's going to turn into its inverse. That's the inverse. Now, how do we say this in terms of homotopies? Well, you watch. Here's my square, and I'm trying to fill it in to create a homotopy. And right here, I'm doing alpha, and then I'm doing alpha bar. So I'm going to write that by putting the arrow in the other direction. So this just means that I run alpha backwards along this part. And now I'm going to make a drawing. And I'm going to tell you what I'm going to do at a given level in this drawing. Let's go up to S. Then I'm going to run alpha up to this point. And this is the same point, all right? So this is some place t. In fact, well, no, I'm not going to do the analytic geometry because of the difference on the two sides. But this is also someplace t. It corresponds to t because of the way I'm parameterizing from 0 to 1, from 0 to 1/2, and from 0 to 1/2. I'm reparameterizing. But this will be basically the same evaluation point. So the value of alpha bar here, but of course it isn't t, it's really t prime, and we're going to have alpha of t is equal to alpha of t prime. So this is running, this is the same as running alpha up to a point and then running it back. Okay? And then how will I map this? This interval here is going to go, the whole interval is going to get mapped over to alpha of t, which is equal to alpha of t prime. So this is a new path which is parameterized on the entire interval, and what it is the following. Up we go, then for a certain period of time, just sit there. That's this period of time. And then we walk backward and come back to the base point. Now, as you see, as I go up higher, I'm using less and less of the curve. Up here, I'm using a little bit of the curve, a lot of constant time. And by the time I'm all the way up to the top, I'm only mapping to P. So this is the construct of the homotopy of alpha star alpha bar to E. Now, I forgot to mention reparameterizations, so we'll keep to that and go back to something more fundamental for a moment. Multiplying paths. What does multiplying paths look like? Well, first of all, I have to tell you how to multiply paths. I told you geometrically how to multiply paths. So what am I going to do? I want to define alpha star beta, taking the interval from 0 to 1 into x. And I know how to define alpha on the interval 0, 1, and so on. So it's quite clear what I want to do. I want on the first half of the interval to do alpha. So that's going to be alpha of 2t for 0 less than or equal to t less than or equal to 1/2, right? And that will run alpha. That will run all of alpha from 0 to 1, but it will compress it into the first half of the interval. And then I need to do beta. And I need to start it at 1/2. And so I want to start at 1/2 at, I want to start at, and that will correspond to 0 for the parameter for beta. And I'm going to go, I'm going to go to 1, which will correspond to the 1 for beta. So I didn't think this through beforehand. So what do I do? I have to take, I need that AT plus B should be equal to 1/2 when t is equal to 0, and it should be equal to 1 when t is equal, it should be equal to 1 when t is equal to 1. So when t is equal to 0, we get b is equal to 1/2. And then when t is equal to 1, we get a plus b, and that should be equal to 1. So a should be 1/2. So this should be equal to beta of t plus 1 over 2 for 0 less than or equal to 1/2 for 1, I'm sorry, for for 1/2 less than or equal to t less than or equal to 1. Check it. If t is equal to 1/2, then you get, oops, I made a mistake. Oh, I did the inverse. Very sorry. We want at plus b, so that when t is equal to 1/2, it should give us 0. And when t is equal to 1, it should give us 1. So a over 2 plus b is going to be equal to 0. And a plus b is going to be equal to 1, which says that a over 2 is equal to 1, which says that a is equal to 2. And then b is equal to 1. So that says that this should be equal to 2t minus 1. Right, let's see. When t is equal to 1/2, I get 0. And when t equals 1, I get 1. There we go. Okay, right. I may have written something a little wrong, but we got that corrected. Okay, so just look at it now. The point is, you do need to do, if you want to actually get used to doing these things, you should do a little bit of the analytic geometry to make sure that everything works right. And then after a while, you're going to stop doing all of it. But this tells you how to multiply two paths, right? And did we get it right? When t is equal to 1/2, we get beta of 0. And when t is equal to 1, we get beta of 1. So this is running beta. Now, I want to claim alpha star beta star gamma is homotopic to alpha star beta star gamma. And then we're in a ballpark of having a group. So this is what the parameterization would look like if you did alpha star beta and then gamma. And this is what the parameterization would look like if you did alpha star beta star gamma, right? So we want to find a homotopy that starts here and ends here. And you see what to do. You start shifting the parameterization. So the parameterization is the one that you would get by iterating this. And you would start here or here, but in the middle, you're shifting the endpoints of the parameterization in the middle until as they move along. So you do alpha a little longer, you do beta, shift it a little bit, and you do gamma, and so on, and you get a homotopy quite clearly that goes from one association to the other. And so we have associativity. And now one last thing, multiplication by E. Here is E, which is always constantly at the base point, and here is alpha. I'm multiplying on the left, on the right. And you want to see that it's homotopic to alpha, and so you just do that, changing your parameterization and staying at the base point for shorter and shorter periods. And as you do here, you're parameterizing alpha for longer and longer periods, but you're doing all of alpha, just running it over a longer parameterization until it's always just alpha. And this is the homotopy of alpha times E equal to alpha. And also E times alpha is homotopic to alpha on the other side. So you see that once you get used to how to make these homotopies, you can see very clearly that the fundamental group is the group. And this is a general construction which works for any topological space, but we're interested, and we want to get to this point before we quit today, we're interested in seeing what it looks like if we are dealing with the fundamental group of the complement of the knot. And so if you're dealing with the complement of the knot, then you see your space consists of all of three-dimensional space except for the knot, and you could choose a base point out here, and you can have curves which wander around the knot. Now I'm going to have to do a little erasure to make this a convincing picture. Okay, so here's an alpha, which is running around the knot, and it's telling us something in the group, in the fundamental group of the complement of the knot. It's telling us something about the way the knot is by the fact that it apparently isn't going to be homotoped off the knot. But what kind of relationships among the elements of the fundamental group are there, and what will generate it? Well, the answer to generation is the following. For every arc in the knot, we'll orient it because we like to have a direction on the loops as well. And then for every arc in the diagram, we're going to run a loop which comes around the arc in the diagram and runs back to base point. So you can think of the base point as high above the plane, and you come down to the arc, and then you go around the arc and come back. All right? And I'm going to use the right-hand rule so that this is the orientation. If this arc is A, then I will call the element in the fundamental group that corresponds to it A as well. And so the arc uses the right-hand rule. The right-hand rule is this, that if you have a loop that goes around an arc like this, and this is by orientation by right-hand rule. Now I come to the fundamental thing that we can do in a minute or two, and then we'll quit. I know we're a little over time. Suppose you have two arcs of the knot running parallel to one another like this. And suppose they add an element in the fundamental group which encircles both of them. All right? Oop. I guess I will obliterate that orientation rule. Maybe there's no need to, but we need a little extra room here. Okay. Now, I want to homotop this loop, and I'm going to homotop it in the following way. You'll see. Yeah. Sorry. Right. So, I hope my picture convinces you that C, the loop that encircles both of them, is homotopic to the product of the loop around B by the right-hand rule times the loop around A by the right-hand rule. Remember, the base point is up above the board, and I just pulled in here and pulled back until I got near the base point, so that first I go around B, and then I go around A, and I'm following my rules. That's the key to seeing something marvelous that's going to be on our next slide, and we'll stop with that. Ah. Whoop. Okay. Here's a crossing. Here's somebody. Let's call him B. And here's somebody else. Oh, I like to call him A. It doesn't matter. But I do like to call him A. And I like to call this one B. And this one C. And now we can apply the ideas that we just worked out. So that means that if I encircle both of these, like that, if I encircle both of these like that, then this loop here is the product A times B. Remember, it was the right loop times the left loop. But this loop here can be deformed, certainly, until it goes all the way around the top part. That's not a problem. But what's this? This is BC. So that implies that AB equals BC in the fundamental group of the three-dimensional space minus the knot. Or in other words, C is equal to B inverse AB. Remember that? That's our quandle operation. So what we're finding out is that the fundamental group has one relation for every crossing. And it is exactly this conjugation relation that we saw was a quandle structure. So that the fundamental group of the complement of the knot naturally is related to the quandle structure that we understood would be invariant. And if you stay at the level of the topology, then it turns out that it is a fact, or a theorem, it is a fact that the fundamental group of the complement of a knot or link in three-dimensional space is generated by the loops corresponding to the arcs in a diagram, and one relation per diagram, per crossing. One relation per crossing, and that's the relation. So with this, we've come full circle from thinking purely algebraically and combinatorially about invariance of knots and links and the quandles over to the fundamental group, which is part of a general scheme for getting invariance of topological spaces. And this general scheme gives us a quandle structure on the knot group, on the fundamental group of the complement of the knot. So if you want to think about something for next time, you can think about the way the structure of fundamental groups looks, starting with the trefoil. Let's just very quickly show that, and then we'll stop. So if we wanted to understand the fundamental group of the trefoil knot, then we can say generated by A and B and C, and the relations are that C is equal to B inverse AB, that B is equal to C inverse AC, and that A is equal to B inverse CD. So that the fundamental group of the complement of the trefoil knot is given by generators A, B, and C, and relations above. And then here's an exercise. Show that G is isomorphic to the group generated by just A and B, such that ABA equals BAB. That's an amusing exercise, easily done by putting in C into the formulas and eliminating it, and just getting the relations for A and B. We'll say more about that next time, and we will also go on to Alexander's polynomial and Jones' polynomial next time. So thank you for bearing with. And I'll stop there.